Good afternoon, everyone. Thank you for being here. The title of the talk is FUOTA using LORAWAN and Zephyr. And by the way, Ashwin, amazing talk. If you attended Ashwin's talk, really inspiring stuff, really good stuff. And by the way, there's a tie-in to mine, so it's almost like I'm a sequel to your talk, and it'll become apparent in a minute. Let's get started. This is our attribution slide. This work has been carried out by myself and my collaborators. A lot of these guys are in India. And of course, the disclaimer is that all the logos and trademarks are properties of their respective owners and are here for identification and attribution purposes only. So let's get started. I'm going to use 4 slides to go a little personal here. This is my own sort of journey, and I call it. It's 4 different phases of myself being a software engineer. In my first 5 years, I call it my indifferent phase, where I used to think that, GNU's not Unix recursion was kind of cute, but that was kind of it. Copyleft, really? No way. Who's going to do that? That'll never work. I used to actually think Next was a much cooler operating system than Linux was. For those of you, it was kind of a predecessor. It's the company that Steve Jobs founded between, being out of work and then being called back as a second coming of Apple. OS2 Warp was an OS that we all used to like a lot, and there was a battle between NT and OS2 Warp back in the day. We actually used to have to pay for C++ or any kind of compilers back in the day, which is, again, shocking, right? It's just about as strange as paying for Netscape back in the day when you had to pay for Netscape. TI, we used to call it Composter, not for a bad reason. GCC was still, I think, on the horizon. It might have actually been around, but we were barely using it back in the day. And SourceSafe, short-lived, and thank God it's over, because it never kept your source safe. Fast forward to my user-consumer years. Was happy when LGPL was created. LGPL, again, was the lesser GPL, which allowed you to essentially use open source libraries without having to essentially give away all of your proprietary code that you were building on top of that. It was sort of a compromise, I guess. I was using extensively and actually modifying OpenAL, not OpenAI. This is back in the days when OpenAL was the open source audio library that allowed you to do 3D audio visualization, place audio in 3D. And so that's what we were doing at the time. Fedora, CentOS came to the Red Hat rescue back in the day. It allowed you to essentially, without having to get an enterprise license, you could actually they would, I think, fork every release, and you would actually be able to use it. My belief then was that everyone was, user communities mattered more than anything else, so it was all about the user back in the day. I started to use a little bit more open source in my production sort of applications. I was using Siren 14, which was Polycom's open source wideband audio codec. It was truly the start of the hi-fi audio revolution. Everyone takes it for granted that your audio calls sound perfect. Not at all obvious back in the day. And of course, the only thing we cared about when Oracle bought Sun was if VirtualBox was going to survive or not. Fast forward to my third phase of being an interested consumer of open source. I started to believe very strongly, and I liked the fact that Android was open source with some caveats. There was all sorts of really interesting forks, Cyanogen being one of them, and we were sort of working with that. MongoDB makes a mean stack. We used to love that acronym and how it was sort of taking over and changing LAMP and slowly encroaching on LAMP's on the LAMP stack, which was Linux, Apache, MySQL, PHP, their sort of hegemony of the market. Again, sorry, Google, you wanted to not be evil, but they've done enough rug pulls, for me at least, to be scarred for life. I was an extensive user of Android Things, which was Brillo, which they then did a rug pull off in 2015. So that scarred me for life. I'm not going back to Google. Google Glass is another one. I started to believe at this point that developer communities mattered a lot more, and really became, more curious to see what people were doing. Still not quite giving back as much as I should have. I stumbled upon Rock Hawkbit. This is from the Eclipse Foundation. Raspbian, of course, was the Pi open source, operating system. And there was a brief foray, at least for me, into Web3, and it felt like it was going to come and save the day. We all know how that story turned out, so I won't bore you with any of those details. And then I think my current state is I would call myself a committed open source person. I'm going to be echoing a lot of the things that you're going to hear, on this conference, starting with our keynotes today. Open standards, protocols, interfaces, all this stuff matters. And it's for the right reason. I mean, I don't think we have to look any further than Frank Nagel saying it's all valuable. It actually is $9 trillion worth of value being created here. Personally, myself, I run a sort of a small consulting company, boutique, doing a lot of embedded stuff. But my mantra now is that assemble, don't rebuild. I don't choose to reinvent the wheel. I don't even choose to actually build something new. I believe enough in the open source ecosystem to now know that almost everything I need exists in some shape or form out there. And the job of a good sort of software engineer in today's day and age is to know how to put the pieces together. You're really just basically putting Lego blocks together in a reusable format. Infrastructure, or the glue logic, to me is code. It's a play on the infrastructure as code thing. So, infrastructure really, for me, is the glue logic, and that's what makes stuff work. And developers need to unite, right? I mean, we gotta watch each other's back. We gotta make sure that we're helping each other out as best as we can, because none of the suits are gonna help. And quality is important, right? Quality matters more than anything else, I think. I think too often we're given this example. Again, typically because the model is you're venture funded, you're going after revenue, you have a chief revenue officer, and it's important to basically move fast and break things and, ship or scale and all that other stuff. It's important, super important, but quality, one should never lose sight of quality. Quality happens only when you are committed to building something and obsess over it. And then, of course, my last thing is I'm being a little cute here. So I've gone from test-driven development to behavior-driven development, which I currently use and I love, to vibe-driven development, maybe. I don't know. Maybe that's coming. Who knows? So anyway, I'll now jump into the actual crux of my talk. Again, first principles here, I'm not making any assumptions about anyone, being an expert here. So what exactly is FUOTA? It's in my title here. So FUOTA is really, it's an acronym, and I've spelled it out here. It's Firmware Update Over-The-Air, right? So you basically have, I think I have a pointer here too. What's the button that works this? This might be it. Oh, there it is, okay. All right, so I think I can get fancy here. So the firmware part is, as we all know, it's the stuff that runs embedded devices, right? Embedded devices won't work without it. And over the air simply means that you're sending this data over the air. And the air is a sort of an all-encompassing idea, but I think for me, the basic differentiation between FUOTA and any other types of DFU, which I'll get to in a second, that's the larger term, which is device firmware update, is that you're doing it without any wires, right? That's kind of the idea. You're sending data, you're sending ones and zeros packaged up over the air. That's FUOTA. Okay, so slightly more complicated, but still reasonably easy to explain. Most embedded devices have chains of bootloaders in them, and again, more historic than anything else. You have this bootloader, which is typically sort of baked in to the, it's from the manufacturer. It never gets. It's literally the thing that when the device powers up, says, "Hey, I'm awake. What should I do now?" And then the primary bootloader typically gives way to the secondary bootloader, which again, actually now is something that you build and ship as part of your firmware image. And again, typically, these are all typical, by the way. This is not by no means, this is a representative, it's by no means all-encompassing. You have your OS slots, it's sort of represented as a slot. And firmware typically means you're shipping both the operating system and the application. So both the kernel and the user space gets bundled up into a single monolith that gets shipped. And you have typical slots. Again, I'm trying to give you the impression of depth here, but there's a slot 1 and a slot 0. And depending on some flag that's been entered from the user space, the secondary bootloader sort of knows to go to slot 0. And then once that comes up, then all the peripherals can come up and start to do the thing that this embedded device needs to do. OK, so let's talk about, again, my title slide is DFU in the real world. Let's talk about what the idealized view of DFU should be. On the left here, I have something called a fleet manager. Again, generally, these are terms of art. A fleet manager is just a piece of software or a function in the cloud whose primary aim is to make sure that a deployed device, again, a fancy way of saying a device that's been shipped, right? It's basically left the mothership. Is up to date. So here we have a firmware artifact whose semantic version is 4.10. And semantic versions are good, right? I'm going to shout out for the SEMVer sort of terminology. They're good. They're open source. They're an open standard. But this has a SEMVer whose minor version is greater than the version that this guy is running. So clearly, it's due for an upgrade. So the idealized view typically, again, is there's some type of state read that happens here. So the fleet manager will sort of say, hey, tell me what your latest version is. What version are you running? And if the state read comes back and says, I'm running 4.02, the fleet manager now knows it needs to do something, because it's the guy who's in charge of, it's the piece of software that's in charge of actually sending an updated version to the deployed device. And that happens through this upload command. The next thing that happens is you want to make sure that the upload was successful. Typically, again, if you're deploying something and you want to be careful and you don't want to have brick devices, you want to make sure you don't do something automatically. So you upload, and there's obviously some integrity checks. You might have a SHA-256 checksum here. But the state read immediately following an upload is the one that actually allows the deployed device to send back to the fleet manager the message that says, hey, I'm running 4.02, and 4.01's been downloaded. What do you want me to do now? And that's when this thing called the state write happens, where you're essentially, as the fleet manager, instructing the device to turn on, or essentially mark this updating this new firmware image as pending or confirmed. Terminology doesn't really matter, but effectively what you're telling the device, or the bootloader actually, is that this is the firmware image you need to use, not this one. That immediately is typically, not immediately, but at some point in the future, when you call the reset command, the device then will go into a reset where the primary bootloader will load up the secondary bootloader. The secondary bootloader will say, I need to now load up whatever's running in slot 1. And again, depending on how the memory map is set up, you might have some elaborate sort of in-place swapping of slots happening before the loading happens. But suffice to say, when this stuff is completed successfully, the device is now booted up using version 4.10, and 4.02 is still sitting in the slot, available for to be overwritten the next time an update needs to happen. Okay, so that's the idealized view of what a DFU ought to be, right? And remember, DFU is just a general case of, FUOTA is a special case of a DFU. FUOTA means just that you're doing it over the air. So what's the idealized view for what a over the air ought to be? So I've focused a lot more on what the actual over the air needs to look like. Of course, you still have the fleet manager and the deployed device. And ideally, you want your FUOTA, your air interface, your transmit. This is a transport mechanism, really. You want it to be lossless. You want it to be stateless, because you don't want to be maintaining state. related to your actual air interface. You obviously want it to be low latency. It should ideally be always on, and these will all become apparent as I start talking about LoRa in a second. And it should be long range, right? Because you want to be able to not have to have repeaters set up to send updates from your fleet manager to your deployed device, right? Now, of course, the title of this talk is FUOTA in the real world, so we're going to switch over to the real world right now. Before I do that, Zephyr RTOS, again, I feel like I'm channeling Ashwin today. It's better than bare metal. That's the journey that most of us have taken. It's modular, it's extensible. Device peripheral management is a lot easier. It's reliable. It's debugging is great, and it's portable because we can create HALs and whatnot. Super powerful for us to do that and easy to use. Okay, now let's come to the air interface part of things. So I, among other things, I've been using, obviously I have a lot of experience using BLE from being an IoT guy. BLE is great, right? Because BLE just works. It's super easy to use. For the most part, it's actually well supported across all hardware and OS platforms. What LoRaWAN gives you is I think more than anything else is just this. It's this crazy sort of unbelievable range. In fact, I think the world record for range is 832 kilometers. Now, clearly, this was a special case, maybe idealized conditions, but you can be rest assured that you can get at least 3 to 5 kilometers, 2 to 3 miles worth of range without really breaking a sweat. And so, what LoRaWAN gives you is a lot of range for not a lot of power, and it's really the ideal. It's one of the ideal platforms for sensors that need to sort of be very long-lived, so they're battery-operated, and they need to be able to send updates once or twice or maybe 3 times a day. So there's a fair number of use cases where this kind of sensor can and should be using LoRaWAN. What's nice about it is that it's stateless. In other words, there's no state to be maintained. Effectively, a sensor will just join a LoRaWAN network and it'll always be on. So it's capable of receiving and sending uplinks. And I'll come back to my nomenclature, but anything that goes from the network side to the device side is called a downlink. Anything that goes from the device side up to the network is called an uplink. There is an always-on mode called Class C, which is really mostly for line-powered devices. And it's pretty energy efficient when it's not in Class C. So Class A and B are the sort of always-on modes. I'm not going to go into them too much because this is not a LoRaWAN session, but suffice to say that one's sort of like it's sort of Class A is when it's just on, and the only time it'll respond to you is when you send it a downlink. So the way to actually have a Class A device respond to you is to send it a downlink. A Class B device will send you, uplinks and start waiting for. I'm sorry. Class A is it'll talk to you. You'll not talk to it. So it's Class A is like, don't call me, I'll call you. Class B is call me between 4 and 6 every day. That's the difference really between Class A and B. Okay, so let's jump straight to the FUOTA standard. The FUOTA standard is published by the LoRa Alliance, which is an open source. No, it's a consortium of manufacturers that make chips and other hardware related to LoRaWAN. And I'm talking specifically about LoRaWAN FUOTA, which is a subsection of LoRaWAN. So it's not the transport protocol, it's the one that deals with firmware over-the-air updates. And these are the good things about it. It's multicast and multiplex, and I'll tell you why that's amazing. What multicast is it's a multicast spec, which means that I can actually have a single session that's sending my update packets to hundreds of devices. So essentially, my statefulness burden is really only As far as my device, my fleet manager is concerned, I'm really only opening one session, but I'm updating hundreds of devices at the same time. In theory, it's also multiplex, which actually means that if I wanted to, I could actually multiplex more than one FUOTA session at a time onto the same air interface. So you could imagine a scenario where you are updating for a system on a chip. You can update both the firmware that runs the app core and the net core with a single FUOTA session. I've never seen this done in practice. I wouldn't recommend it. It has built-in forward error correction, which is again kind of cool, because you realize that LoRaWAN's a lossy. It's very, it's prone to loss, right? Because it's a wireless, low-powered, long-range air interface. So it's kind of nice that this is baked in. You don't actually have to do any error correction of your own. No retransmits required. It supports both class B and C. Again, I'll come back to that. One's an always-on class. The other's sort of like a timed class. And it's quite supportive and active, in terms of its user base. This is the repository that is maintained by the Semtech folks. This is an open source implementation of the LoRa Basics modem, which we base everything on. All of our code is based on this. This is an LBM Zephyr port, so this is effectively an app that's building this on top of the Zephyr OS. So this is an LB. It has a West, and these are the boards that it supports. So it supports a reasonably comprehensive list of boards. Here's the bad. Okay, the bad is that it assumes that all your artifacts are 200 kilobytes or less. It doesn't really do well with artifacts bigger than that. So bare metal, 200 kilobyte artifacts, no problem. Nobody's breaking a sweat. The minute you start to add Zephyr to the mix, it becomes a little harder, right? Because Zephyr's got its own little nice, arguably very nice and useful bit of overhead that probably starts to drive this to the 300 to 600 kilobyte range. And then the minute you start to get fancy with some of your actual embedded features, you can actually easily get up to about 900 kilobytes, maybe even a megabyte. And that's where this really starts to break down. There's these sort of incompatibility issues. They've published 2 different versions. They're completely incompatible. In fact, not only are they incompatible, there's unexplained behavior if the node and the application server are different versions. Again, I'll leave it up here if you want to talk about it some more. I'm happy to discuss more. But the FEC-related, there's some redundancy overhead that's imposed on you. So effectively, as the block size, or in other words, the actual artifact size, as you're trying to send more data over the air, the burden it actually imposes on you for sending redundant fragments, which are needed for actual success in real-world conditions, starts to climb. So again, as your data block size goes from 1 kilobyte to 40 kilobytes, in theory, you might have an overhead percentage of almost 50%. So you might actually have to transmit almost half as many packets just to get a reliable sort of delivery confirmation. Okay. Okay. And here's the ugly. The ugly is it's got way too many parameters. So if for someone who's basically just trying to use LoRaWAN FUOTA as a transport, maybe like BLE or UDP or even HTTP, this is not what you want, right? You don't want to have to tune all of these every time you're trying to transport a blob. Not a great idea. And what I like to tell everyone is that it's missing a management layer. There is no management layer. It's almost like imagine if you had to basically do HTTP, but also have to worry about the TCP parameters of the transports you were sending. Bad idea. This is where it's at today, okay? There's a whole bunch of inefficiencies related to Class B, which I'm not going to get into, but I'm just going to jump straight into the Rube Goldberg architecture that I've had to come up with. And again, I apologize. I spent 5 minutes talking about this. And then I'll tell you, each of these are open source. Everything here that you see is built using open source components. There's a star list that we publish that you can download and build your own. So everything here is open source. And the SMP manager stands for, SMP is the SMP protocol that ships with Zephyr. It's a subsystem. It's actually part of the MCU manager subsystem. And by the way, This BLE subsystem that talks to the BLE GAT server on the net, this 5340DK, this is likely the same thing that Ashwin uses for his updates. It's the BLE, and this works. This is just solid. This is rock solid. It just works. Okay, we're using SMP Manager, which is an open source CLI from the folks at Intercreate, which allows you to basically take a firmware and send it over BLE to this dev kit. Okay, this is a 5340 dev kit. What we have done, is chosen, much like Sisyphus did, to use this same paradigm to break this firmware into blocks that are about 4 kilobytes long and send it over, essentially treat that 4 kilobyte block as the MTU for a new transport that we've written, which we call ChirpStack FUOTA, that utilizes all of this technology to achieve the same goal, right, that this is doing. But instead of actually using a single protocol, which is BLE, which is what you need, all you need is the BLE protocol, which has I think the MTU is about 256 bytes or 400 bytes, whatever it is. It's configurable. Instead, we have to use all of this stuff, again, sort of because of the nature of the beast here, which is that LoRaWAN works through what's called gateways. So really the last mile or last 5 or 10 miles are the LoRaWAN protocol. The rest of it is this is all cloud. Okay, so we're actually talking UDP between the LNS and the gateway. We're talking gRPC between the application server and the LNS. There's a little bit of MQTT and HTTP thrown in between this guy and the LNS. And even though it looks like a Rube Goldberg machine, it actually works pretty well. So again, a little bit of a primer on what the MCU manager is. It's the implementation of the SMP protocol. It's sort of the de facto device management system within MCU, inside Zephyr. It's an evolution of Newt Manager, which is again from the Apache Foundation. So again, if it's not obvious, this is me being, super appreciative of open source. This is just, I'm a convert here, guys. It's available on most downstream Zephyr distros. It's robust and hardened. I think all of us know what hardened means here in this context. It really has the feeling of something that's been used extensively. It actually is pretty extensive. Zephyr only implements a few of these, but the one that we care the most about is this application software image management group, where you get all of that stuff. So if you go back to my idealized slide, this is the group that we use, and these are the sets of image. These are the commands we use. We actually have an image upload command. We don't actually even use the image arrays, but you could technically use it. But then what we end up using are the command ID 0 and 1. The state of image, and the image upload. This is the SMP manager, SMP client, SMP library, sets of libraries from the folks over at Intercreate. Again, shout out to them. What we've done effectively is added a new transport layer to this CLI, where you can essentially just take a ChirpStack FUOTA transport. In the past, if you were not using our fork, you would only see BLE, and with BLE, you just have to specify the Bluetooth MAC address you need to connect to. But again, if you've been using SMP Manager or the MCU Manager, you'll be quite familiar with using the Bluetooth GAT server that's actually implemented to transport DFU to transport artifacts for device firmware update. Okay, let's see here. ChirpStack. Anyone who's actually done any work with LoRaWAN will know that ChirpStack, aka Brokar, who's actually the developer, I think he's the sole maintainer of this thing. He's one of the most prolific open source guys I know. He updates this, weekly, if not daily. It's really the de facto open source LoRaWAN network server. It's written in Rust. And then, as if that wasn't good enough, he actually implemented a FUOTA application server of the FUOTA 1.0 spec in Go. So he's got Rust and Go, because he couldn't choose between the two, but I think he's more of a Rust guy. And Semtech, again, shout out to Semtech guys, because they are the maintainers of the LoRa spec. They actually make the chips. That's how they make their money. They're a hardware vendor. But they've done a pretty good job with prodding from folks like me and others, of course, to open source a lot of their sample code. So LBM Zephyr is their port of just essentially, you literally can just build the entire LoRaWAN basics modem with a bunch of sample apps on at least, well, most of the Nordic hardware plus a bunch of the STMs. So it's a great starting point if you're looking to basically, play around with sensors and LoRaWAN. Anyway, so our little contribution to this is this little file here called smplbm.c, where we've essentially we've wedded these two worlds together. And this is the part that I love again about open source, is that we've taken a hardened part of the Zephyr subsystem, which is the MCU manager, and married it to the LoRaWAN side of things to create the smplbm.c. Specifically, we're also using FUOTA multicast downloads to send our packets down. And of course, last but not the least is the Nordic guys themselves, as we know, again, from Ashwin's talk, that they've been contributing and made sort of, I think Zephyr has become hardened, I think in large part because of the contributions of the Nordic guys. Zephyr works out of the box with them. There's some confusion around all the sort of downstream repos and forks they have. There's various flavors, not just even of the NCS. There's the official NCS SDK, then there's the SDK Zephyr, which is their downstream, which is sort of halfway between Zephyr and NCS. I have to say that even as SMP LBM was inspired by and based on SMP LoRaWAN.c, which is actually something that Nordic has added to their fork, actually has now ported all the way back upstream to the Zephyr RTOS. It's actually there if you go read it. This file exists today in the top of the Zephyr RTOS. The only difference between what they did and what we've done is that they just use your sort of, let's call it vanilla LoRaWAN downlinks. So unfortunately, when you do that, you're limited to 242 bytes. You can't really go any higher than that. So you're sort of sipping through a straw, and you're limited to 242 bytes. What we've done with our implementation is, because we're using and leveraging FUOTA, which is another LoRaWAN standards, we're not limited to 242 bytes. We can actually, in theory, go to 40 kilobytes if we wanted to. So we now have a transport that has an MTU that's limited only really by sort of design considerations. Okay, so I think I'm almost done here. I'm ready to wrap up. Device firmware update in the real world, Act 1. We do a West build. We use NRFJProg to build it. We flash a Nordic dev kit, which is running an SX1262 based LoRaWAN card. We have it join a ChirpStack LNS, okay? In Act 2, we actually do the OTA. We do a West build, we get a 410. We use SMP Manager to send this image up via the ChirpStack FUOTA application server using a deploy. And this deploy is actually, what we're doing is really chopping this up into 4 kilobyte chunks, and it's sort of going round in circles until it's done, okay? And then the last act is what I showed you before, but now I'm actually doing it using real commands. I'm doing the state read, the upload, state read to confirm that the slot's been written, the SMP manager state write to basically confirm the slot, and the reset. I might have run out of time. How much time do I still have? I got 1 minute to go? Okay. Okay, so great. Wow, I think I may have timed this right. Please bear with me. I'm gonna do a Steve Jobs thing and say one more thing. Okay.
You have 6 minutes.
Oh, I do have 6 minutes. Is there a reason why this is not showing up here? Sorry. It's on my screen here.
might actually have to take this here.
Or you want to do a mirroring or something?
Yeah, you might have to actually mirror that. Yes,
Okay.
indeed. So I think you have to extend it, right?
Should I try plugging it in?
Sure.
Okay, so while this is playing, I just want to. This is just me doing my first run using the SMP manager. And I'm using Bluetooth here. You might be able to see this. I'm using the Bluetooth transport. And imagine my surprise when I see this happen. I'm sending an upload here, and you'll see in a second why I literally started dancing a jig when I saw this. It's connecting to the GAT server, and it just literally jumped to 29%. And the reason it did that is because the SMP protocol actually has, for free, resume and pause in it, okay? Didn't expect that. That was a gift. That's the open source gift I got. It was amazing. I mean, it was truly a magical moment. But wait, there's more. It doesn't end there. What I was able to do with the same command is I was able to switch transports. And now you can see I'm actually transporting using chirpstack FUOTA, the same session, and it picked it up where I had left it off. So effectively, I was able to switch transports in the middle of a single DFU update. And it worked, just worked. And my journey as a convert was complete. Thank you. I think we have time for some questions. Go ahead.
So the receiving side is the chirpstack LNS, that's an application that receives, that runs the DFU protocol.
Yes.
It's not something that would run in a bootloader decoupled from like Zephyr.
Okay, let me just rephrase that question here. Let me replay the question you had. Hold on. Are you asking, what's the question you're asking about? Okay, let's go back to this. This is a great point here. So you're asking if this is, or you're asking if a question about this?
It's just the LNS, that's an application.
Okay.
It doesn't run in a bootloader, right?
No. So I'll repeat the question here. The question was, does this run in the bootloader? And the answer is no. The only thing that's actually running inside the firmware is here. And you can see that with the Nordic dev kit, this is a system on chip. All that needs to be running here is this SMP server, which again is part of Zephyr. Zephyr has an MCU manager subsystem that ships with every, I think you can turn it off if you wanted to as from the kconfig files, but mostly you don't, because I don't think it actually adds a lot of. Does that answer your question? Okay, thanks. Yes?
So you mentioned the existing protocols having limitations on like payload sizes.
Yes.
So the modified version, is that something that's going through standards track? It's just a different standards track? Like, this sounds very cool. Where's that at other than just like this?
Yeah, it's a good question. The question is, the existing protocol, I mentioned in my talk that the existing implementation that's actually, at least in Zephyr, limits it to the 242 byte limit that sort of LORAWAN imposes, and is there some effort to put this into the standards track? So I'll answer that question in two parts. The first part of that, the first answer, part A of that answer is, the FUOTA spec is already part of the FUOTA, the LoRaWAN suite of standards that addresses how to send payloads greater than 242 bytes. So you can send, in theory, payloads of a kilobyte, hundreds of kilobytes, okay? What they don't address, and where the incompleteness of that spec is, that they don't give you an end-to-end use case of how to, here's how to basically take a blob, which is a firmware image, send it across to a device, and have the device sort of do the right thing. It's more of like here's a blob, and here's a set of specs that let you transmit that data. So I don't know if that answers your question, but the short answer is there are specifications in LoRaWAN that cover sending larger payloads. They're just no one's sort of tied a bow around everything together and made it easy to use. So this is our attempt at basically giving back to the community. Yes, please.
I have a question around the same lines of this is the version that you have distributed to Semtech with LoRaWAN. What will it take for you to upstream that into Zephyr?
So again, I'll repeat the question again for the folks who are listening later. Is this something that we can upstream to Zephyr? I think the answer is yes. In fact, I would love to see that upstream to Zephyr. My fear is that because of the nature of this Rube Goldberg contraption, people might balk at it. And so the reason is, even though every little component here is open source, the fact that in order to just basically get an upstream, this firmware updated, instead of, see, with BLE, I'm sorry it's hidden here, but BLE only uses one type of transport mechanism. It's just one. All you're doing is basically connecting to a GAT server on the device here. Okay? With this, someone inside the Zephyr community might say, well, this is too complicated. I mean, is there not a simple way? So I'll take it up. I think I do want to make this upstream if I can, but I'm going to go stepwise. I'm going to first get some of the guys who maintain this, the SMP manager, CLI. I'll go talk to Brokar, who's the chirp stack maintainer, and then I'll maybe get to the Nordic folks. Anybody else? All right, thank you very much. Appreciate your time today.